Hello. So I'm Jon. I'm from Veridise. We are a security company, and we secure many types of things, particularly ZK circuits. And lately, we've been focusing a lot on these ZK VM applications. So we've worked with RiskZero on securing their ZK VM. But lately, we've also seen an uptick on the number of people developing on that ZK VM. And so today, I'm going to talk a little bit about things that you might want to consider if you want to integrate a ZK VM into your ecosystem as like an L2 built on top of a ZK VM or into your DApp. Okay, let's see. Is this? Oh, that's the button. Okay, so let's talk about what a ZK VM application is going to look like. You're essentially going to have a user. That user is going to want to prove some computation on the ZK VM. So what they're going to do is they're going to provide an executable, and that executable is going to be provided to the presumably RISC-V ZK VM. And the RISC-V ZK VM is then going to prove that that computation was executed correctly, and it's going to include other information about like information that you want to make public, and then that is what is going to be included in the proof, which is in the next step. And then finally, you can verify that proof somewhere. So this can be done on chain. It could alternatively be done by just providing someone with the proof and allowing them to verify it. So to some of you, this might look very similar to another type of application, which is a ZK circuit. And so ZK VM applications are going to look like ZK circuits because obviously a ZK VM is built on top of a ZK circuit. But it's kind of a general purpose ZK circuit that lets you prove kind of arbitrary computation. And so when we look at security risks, one thing that we can do is we can start, by looking at security risks in a ZK circuit itself, and then kind of abstract away from that to say, like, what do we inherit from ZK? Like, what security vulnerabilities do we inherit from ZK? And maybe what are some new security vulnerabilities that we should be aware of? And so that's what we're going to do right now. So we're going to start by just looking at ZK circuits versus ZK VM applications. So if we do that, we kind of get a breakdown like this. So we can look at a number of different things, or a number of different metrics to compare a traditional ZK circuit against a ZK VM application. So first of all, if we look at the language, typically when you are interacting with a ZK circuit or when you're writing a ZK circuit, you're writing in some custom DSL or EDSL, where an EDSL is just basically embedded into another programming language like Rust or Go or something like that. With a ZK VM application, though, you're writing you can write in a general purpose language. You don't have to write really any sort of custom code. You don't have to worry about learning kind of a new programming paradigm. You can just write your program and then execute it on a ZK VM. That's kind of the promise of the ZK VM. Then what the ZK circuit is going to prove is when you write your ZK circuit, you're essentially going to write a bunch of constraints that say, if these constraints hold, then I should produce a proof. And so really what the ZK circuit is proving is just constraint satisfaction, that someone knew how to provide a satisfying assignment to those constraints. With a ZK VM application, though, you're actually verifying the correct execution of whatever the input image is. And the input image would be the program that you're executing on the ZK VM. Then, if we look at things like the number of available resources or libraries that you have access to, because ZK is relatively new, we don't have access to a lot of general purpose libraries to perform things like execute the EVM, things that a lot of people want to perform inside of ZK. However, with a ZK VM application, you kind of have access to a lot of libraries because now you don't have to worry about someone writing a general purpose or a very specific implementation of a library for a ZK circuit. So you can inherit like Reth or really any sort of library that's available in the language you're developing in. Then, if we look at the amount of specialty knowledge, writing a ZK circuit is going to require specialty knowledge because not only are you writing computation, but you also have to write constraints in order to make sure that computation is checked appropriately. And so this is something that's new to a lot of developers because there's not very many languages or really no languages that you have to do this unless you've interacted with something like an interactive theorem prover in some ways, or a language like Ivy, or another language similar to that, where you're proving some information about a program. With a ZKVM application, though, it doesn't really require any specialty knowledge. The only thing that you need to know is how to divide up the ZKVM, because sometimes they've got kind of assumptions about what goes where you have like in RISC-0 parlance, you divide up your ZKVM application into two parts, a host and a guest. But really, the host doesn't matter because it's not proven. So the only thing that we really care about is the guest. And so that really doesn't require any specialty knowledge. The host just needs to gather any information you need. The guest just executes everything. And then finally, we can look at performance. And so this is something that a lot of developers care about, where a custom ZK circuit will typically be faster. However, I have an asterisk there because it typically still requires a lot of work. You have to perform constraint optimization and stuff like that the ZKVM might have done for you. They also have typically done a lot of work to make sure that they can accelerate the ZKVM itself, which you don't have to do then. But generally, a ZK circuit has the potential to be faster, or it typically is faster, whereas a ZKVM application is typically going to execute slower, or it's going to require more resources. So with this overview, we can start looking at some of the bugs that we might have inherited from ZK. And so to do that, let's start looking at some of the common vulnerabilities that we find in ZK circuits. So in ZK, there's a number of bugs that at Veridise we very commonly identify. So the first one is under-constrained circuits, where an under-constrained circuit essentially allows anyone to add a value into your constraints, or to say that a proof was generated, but with a value that you maybe didn't expect, because essentially the value was not constrained to be deterministic, and so essentially someone could just inject a value that you didn't expect. It wasn't inside of your witness generator, and as a result, your proof is now proving something completely different. With another thing that we often find is an inconsistent witness, where your witness computation is different from your constraints. And so in that case, an under-constrained circuit is actually a specific instance of this, but an inconsistent witness also includes things like over-constrained circuits, or just places where the behavior encoded in your constraints slightly don't agree with the behavior encoded in your witness. Then we have something like a proof replay attack, where a proof replay attack simply allows someone to verify a proof multiple times. This isn't something that is necessarily unique to a ZK circuit. It's not a property of your ZK circuit. It's more a property of how you're using the proof as the output of your ZK circuit. But since typically people expect proofs to be unique, they often want to make sure a proof can only be verified once. And you often have to encode some specific behaviors to ensure that's the case. A next thing that we often see is missing input validation, which simply corresponds to cases where someone takes something as an input and they expect that it's going to have a certain property, and they don't check that that property holds somewhere else. We also often see privacy leakages, where one reason why people use ZK is for privacy. That's not only for scalability. And so if someone can infer private information, then you have a privacy leak. And then finally, the most common issue that we find are logical errors, which just basically corresponds to someone encoding some logic that doesn't actually meet the behavior that they expect to be encoding. So now that we've kind of gone over these pretty much as fast as I can, let's go ahead and take a look and see which of these bugs can happen in a ZKVM application. So this is what I came up with. Basically, shields mean that you are now safe if you're executing in a ZKVM, and bugs mean it can possibly happen in your ZKVM application. So the reason why those first two, you don't have to worry about those first two instances, is because we've kind of divided the responsibilities with the ZKVM. Because the ZKVM itself is supposed to ensure that that's the actual circuit that's being executed. It ensures that the RISC-V circuit, if we're talking about like RISC-0, is actually constrained. It's doing what it's supposed to. And so you can rely on the security guarantees given to you by the ZKVM. But there are many other things that you still have to deal with, which you also have to do with a ZKVM or with a ZK circuit. So now we can go and look at a couple of these vulnerabilities. So we're just going to look at a selection, and we're going to look at how ZKVM applications can actually exacerbate these issues as well. So let's take a look at missing input validation. So like I already said, missing input validation occurs when you have some specific relationships that you expect to be enforced within your zkVM application. So for example, the person on your left is saying that I have a value x, it's 5, and then they also have to input the hash of that value, which they're also claiming is 5. And so they perform an executable, which presumably is supposed to check this, but if they don't, then essentially that can be verified at the end of the day. So your zkVM application can't assume that specific relationships hold, and you kind of have to decide where you want to verify certain relationships. So you can do so inside of your zkVM itself, or at the point of verification. And we'll talk a little bit about how people end up deciding that. But essentially, zkVMs exacerbate the issue that we saw in zk circuits because they often have much more complex relationships between their input variables. And so let's take a look at an example. So through a lot of this presentation, I'm going to talk about RISC-0 Steal. That's essentially a library developed by RISC-0 in order to prove some computation about the EVM. None of these vulnerabilities are actually in Steal. It's just a good thing for me to point to because it's sufficiently complex. So with Steal, you might want to say, I have a certain transaction. I want to prove something about that transaction, and this is the block number I want to prove it on. And so in order to do that, this is essentially the steps that it has to take. So first of all, during the process of invoking the zkVM, it has to fetch a bunch of information required by the EVM itself. So it needs the block header, it needs information about the state, it needs information about storage, information about previous blocks accessed, and then also the bytecode that's being executed during that transaction. Then what Steal is going to output is it's simply going to output an REVM configuration. So this is just basically a number. And it's going to output a block number and block hash. So you can notice that what is going to be included in the proof does not include all of the information inside of the invocation to Steal. And so that's where we kind of have a problem, because we can validate some of that information on chain, but it depends on what's included in the proof. So essentially, we have to make sure that all of the information that is provided to your zk EVM is consistent with what is going to be encoded in the proof itself. And so because we're providing like a block number and a block hash, essentially you have to ensure that all state accessed is equal to the state within the block number. And you do that by computing a miracle trie and ensuring that the root is correct. And you basically do that for all of the different versions. You recompute how that is going to be represented in the block header, and you ensure all of that information is consistent, because then your block header, or the hash of your block header, essentially gives you a very good summary of the computation performed. So essentially what we need to do here is the zkVM application itself needs to ensure that all of this information is consistent. And so if this is missing, then essentially what someone could do is they could execute this transaction, but on very different state. And that's what we want to avoid. Okay, so the next thing that I'm going to go through really quickly is a privacy leak. So a privacy leak occurs when someone has information that they expect to be private, but when verifying the proof, someone can somehow learn that information. So essentially, in this case, the user has a value x. They expect that value to be private, but then at the end of the day, when things are verified, that private data is somehow learned, and they can make it public. So essentially, the zkVM application itself can be used for privacy, but you need to make sure you consider how information is going to be represented to make sure you aren't leaking any of this private information. And then zkVMs also kind of exacerbate the issue of privacy leaks because a lot of people want to execute a zkVM application using like a proving network, but in that case, all of the public input that you might expect to be private is going to be provided to the prover, and so then the prover will learn your private information, and they could possibly leak it or use it in some adversarial way. So let's take a look at an example again. So again, I'm going to use Steal. Steal itself is a library, and so anyone can instantiate it to prove information about a transaction on EVM or on the EVM. And so in this case, let's say someone wanted to prove information about the events that were emitted during a transaction, but they don't actually want to, provide any information about the transaction. So in that case, the user provides some secret transaction. The invocation process is going to include everything that I talked about before, gathering state, providing it to the ZK EVM. And then finally, the proof itself is going to include some information, but not the transaction. So it's going to include the block hash, the block number, the things that I talked about previously. But now let's say they also include the events. And then on-chain, someone wants to verify this event was actually included within that execution. So an event was fired. The problem that you have is that in a lot of cases, people emit events very liberally. And so anytime there's some sort of significant state transition or something like that, an event is going to be emitted. And so it's possible that if someone is not careful about the types of transactions that are being executed in this ZK EVM, another individual can learn the transaction that's being executed by simply inspecting the event log and using the information contained within that log to reverse engineer the transaction itself. And so it's important to consider, in this case, like exactly what information is going to be included in your public data that's in your receipt, and how that might be linked to private or information that you want to keep private. Okay. So now let's look at some new vulnerabilities. So the first thing that I'm going to talk about is imprecise error handling. So essentially the way that a ZK VM typically prevents a valid proof from being generated is by simply throwing an error. So it will panic. And so that means that now panics become very important, and ensuring that applications are panicking in correct locations is very important. And so essentially what we want to ensure is that when an application should not actually generate a proof, it's panicking, because otherwise it will still generate a valid proof, and that proof could be verified on chain or wherever you want it to be verified. And so for that reason, you have to reason now very specifically about the cases in which your application is panicking and make sure that you're only generating proofs when you're supposed to. So essentially, you now want to make sure that your application crashes specifically when you want it to, and crashes are the behavior that you intend. So as an example, this is Rust code. It's, again, how one would typically invoke steal. And you can see two different lines. The first line is wrong. The second line is right. For those of you who write Rust, you'll probably be able to see why. But basically, in the first line, you're invoking a particular function, but that function is going to return a result in Rust parlance. And a result essentially can include an error. And so in this case, if the specific transaction that you're invoking errors or reverts, you likely want to also panic so you don't generate a proof. And so in the first case, if you do not do anything with that error, then all of a sudden your ZK VM application will, generate a proof, and it could be verified on chain. In the second case, it's going to panic, and then, everything will presumably work correctly. And so in this case, Rust has some nice features, and results are actually wrapped in this particular thing called must error. However, this only generates a warning. So now warnings in Rust become very important, because if you aren't handling errors correctly and you ignore the warning, then all of a sudden you might be verifying things that you don't intend. Okay, so the last thing that I'm going to talk about is supply chain attacks. So this can happen in a ZK circuit as well. However, because ZK circuits are so new, there's very few libraries that are available for them. And so most people end up writing pretty much all of the logic that they need in their ZK circuit themselves. However, with a ZK VM, you now have access to all of these particular resources. So for Steal, for example, Steal includes references to REVM, Faraday, Alloy, BigEnt, and if any of these have errors, then the computation that you end up proving might not be correct because the underlying program itself is not correct. And so that means that you have to be very careful about what you're importing and what dependencies your ZK VM application actually has. So because of this wider variety of applications, you now have to be, or the wider variety of libraries, you have to be very careful and make sure you're only using trusted resources. But also, you kind of need to plan ahead about what happens if something that you rely on or one of your dependencies has a bug. So as an example, we can go and look at some bugs that have been found in popular libraries recently. So this year, a bug was found in Greth. Last year, a bug was found in Greth. This year, or let me see, date, last year, a bug was found in Alloy. Another bug was found in REVM, and so on. And so that means that any of these bugs could now affect your REVM application. And so you need to plan ahead about how you're actually going to mitigate any of these if it can impact your application itself. And so what I mean by this is having a migration plan. So you can migrate from one instance of your ZKVM application to another one very quickly and allow people to actually check and make sure that you are working with the most recent version of your dependencies that have all of the security patches available. Okay, and that's all I'm going to talk about today. And so, yeah.